Ladies and gentlemen, class recording has started. I will erase this zero point note so it doesn't haunt you the whole period. So. All right. Yesterday, we introduced Newton's first law and Newton's second law. Like it says, important concepts dealing with force and what force does. So first, let's review quickly. Force. What are forces? Any?
A push or pull on an object.
Push or pull on an object. More importantly, what do forces do? Connor, go ahead. How about instead of change the acceleration, let's go cause acceleration, right? Changing acceleration means that it's changing the rate at which it speeds up, right? A little bit different, but let's just go with causes acceleration, okay? All right, that being said, then we got into Newton's first law and Newton's second law. So Newton's first law basically gets summarized in one word. What is that one word that summarizes the gist of Newton's first law? Inertia, right? And if you look up here, there it is, right? So what's the gist of inertia? Is the gist of inertia? Explain it to me. Mark, go ahead.
An object will want to continue what it's doing unless something else causes it to do otherwise.
Good. An object will continue what it's doing, if we're talking about it in terms of motion, right? Will continue in its motion unless it is acted on by a net force, right? Okay. So continuing its motion, right? Sorry, let's go with this. Continuing its motion means that it could do what or it could do what? What are the two options for continuing its motion?
It could be sitting still or it could be moving.
Moving how?
At a constant acceleration. Constant velocity.
Constant velocity, right? So it could either be at rest or it could be moving with a constant velocity. And yesterday I think we made mention a couple of times that something moving with a constant velocity, two requirements, right? What are the two requirements? Same speed, same direction, right? All right. If something is at rest and remaining at rest or moving with a constant velocity, we gave it a term yesterday. What did we call that? We said that an object is in what? Nick? Equilibrium. Nick, what's the actual condition as far as equilibrium is concerned? The acceleration of the object is zero, which also means what else has to be zero? The net force, right? The net force being the combined effect of all of the forces, right? So that means that an object that has a net force of zero has to have at least how many forces acting on it? If it had one, would there be anything to cancel it out? So it's got to have at least two, right? Sometimes it will have lots, okay? But it has to have at least two, right? So when we add them up, we get zero. That requires then what has to be true about those two forces?
They have to be equal.
They have to be equal and
Opposite, like one positive.
one positive, one negative. Equal in magnitude, but opposite in direction, right? So one's positive and one's negative, okay? All right, good on Newton's first law. Newton's second law. Newton's first law deals with inertia, and that's things staying the same. Newton's second law deals with what? What does Newton's second law summarize for us? Newton's first law deals with inertia. Newton's second law deals with what, Nick? Acceleration, or more generally, things doing what? Changing, right? That's a better term for acceleration. Something can be moving without accelerating, right? Okay. So Newton's first law deals with things staying the same or not changing. Newton's second law deals with things changing, right? Two things affect the acceleration of the object. What are those two things, Andy?
Mass and net force.
Mass and net force. What kind of relationship do mass and acceleration have? Okay, good. Inverse relationship. What kind of relationship do net force and acceleration have? Your options are kind of limited, right? If mass and acceleration are inversely related, direct relationships, right? Net force and acceleration. And, right? Okay, so that shows their words. And yesterday I gave you an equation right at the end of class that summarizes those two mathematical relationships. And what is that relation, or what is that equation that summarizes those two relationships?
Acceleration equals net force over mass.
Acceleration equals net force over mass, which is one way to say it, or the other way we can say it is
Net force equals mass times acceleration.
net force equals mass times acceleration. There it is. Okay? Maybe not the most famous equation out there, okay? I'd say E equals mc squared is probably a more famous equation, but this one you'll use a lot more. So that's where we're headed today. Okay? All right, questions? We good there? Let's start off today on concept development, practice page 4-1. So concept development, practice page 4-1. I would like you to start off and discuss with the person next to you the answers to questions number 1 and 2 on the front page. So concept development, practice page 4-1, questions number 1 and 2. Let's take a couple minutes, discuss those, and we will come back and discuss together. Go. All right. Up on the board are the answers to the first 3 questions. I'm assuming the first 2 were pretty easy, right? Okay. The second one may be a little bit trickier. Okay. Are we good with why it's path C? If you're not good, please raise your hand. Okay. So, Lauren, going back, and Lauren, I know you're not the only one. Okay. Going back to the last section, right? We said that acceleration can take 3 forms, right? What are the 3 ways that something can accelerate? Speeds up, slows down, changes direction, right? Something moving in a circle is constantly doing what? Constantly changing directions. It might not be speeding up and it might not be slowing down, but it is still accelerating because it's changing directions. And that's easy to see if we look at it on one side of the circle versus the other side of the circle, right? Over here it's going this way, but over here it's going that way, right? Okay. That being the case, that only happens, it's accelerating, and we said that in order for something to accelerate, what has to act on it? An outside force, or actually, based on our discussion from yesterday, maybe we go with net force, right? Okay. In the case of this ball going around the circle, what causes it to go around in the circle? You are whirling it, right? But you aren't actually touching it, right? What's touching it, though? So, right? Right? What causes this ball to go in a circle? I'm moving the string, right? But if the string's not touching it, does it go in a circle? Ready? So, something that's going in a circle is constantly changing direction. And it will continue to change direction as long as something is making it change direction. In the case of that, as long as the string is attached, it will keep changing direction. But if the string goes away, or if I stop holding the string, or if the string gets cut, now inertia takes over. And inertia tells it to do what? Keep going in straight line, constant speed, right? Constant velocity, right? So when this object is spinning around the circle, when it gets to the top, right? If it's spinning around a circle like this, right? At this point, it's going this way. And at this point, it's going this way. And at this point, it's going at this point, it's going this way, right? If there isn't anything there to force it to do anything different, what will it continue to do? Keep going that way, right? That's the whole idea of inertia, right? That whatever what's doing right now, it's trying to continue doing it right now, unless something makes it change. But if there's nothing there to make it change, it won't change. All right, good there? Okay. Let's now slide a little bit now down to this guy on a bus dropping his pencil. So go ahead and do question number 3. Might be a good idea for you to talk about this with the person next to you. And we'll come back and discuss together as a group. So number 3, there's like 4 questions to go along with it. Ready? Go. Okay, let's discuss. This example of this guy on the bus holding his pencil is the same example, right, as me walking around the room tossing this ball up into the air like this. Okay? Or, man, I won't go there. One second. All right, so I'm walking across the front of the room holding this ball. Because of that, the ball is moving. So, inertia says that ball is trying to continue moving in a straight line, okay? Unless it's acted on by a net force. So in this case here, I could walk across the front of the room and do this, right? So I'm walking across the front, toss the ball up in the air, catch it again in my hand, okay? Was the ball acted on by a net force? Yes, that net force came from where? My hand first, right? Okay? And then, as soon as it leaves my hand, what's acting on it? Gravity, right? So it slows down and then speeds back up on its down trip, right? And ends up right back in my hand. Except, originally this ball is moving which direction? Horizontal or vertical? It's moving horizontal, right? But my force of throwing the ball up in the air and then gravity act on it which way? Horizontal or vertical? Vertical. Vertical forces can't change horizontal motion. Vertical forces change vertical motion. So the ball goes up and comes back down. But the whole time it's going up and coming back down, what is it still doing? It's still moving forward, or it's still moving horizontally. Why? Because nothing changed it from moving horizontally. So it stays with me as long as I keep doing what? As long as I keep moving horizontally. Suzanne, how would I have to keep moving horizontally though? Say again? By walking, how fast? Right. As long as I keep walking horizontally the same speed that the ball keeps moving horizontally, we'll end up together again, even though the ball may go up and down, right? I could do this, right? Didn't catch the ball that time because I stopped, right? Or I could do this, right? Right? Or I could do this. No, you ready? You catch it on the way by, right? Right? In all 3 of those situations, the ball didn't end up in my hand, right? But because there was some acceleration involved. I slowed down, I sped up, Noah stopped the ball, right? Whatever it might be. But if any of those accelerations don't happen, horizontally it will keep going the same rates, even though it might be changing vertically. Good there? Are we good with the answers up on the board? Another example. does it matter how fast we're going horizontally? Is this experiment any different whether I'm standing still, whether I'm walking this fast, whether I'm in a car on the highway going 70 miles per hour, or whether I'm in an airplane going 500 miles per hour? As long as what? Go ahead, question.
As long as it's a constant velocity.
As long as there is no what?
Air resistance.
Which would be an example of a outside force or net force, right? As long as there's no net forces, it doesn't matter how fast we're going, the experiment works exactly the same, right? Eric, were you answering that question, or do you have a different question?
Okay, well now I have a question. Okay, wouldn't air resistance be in that force?
Yes.
So this experiment doesn't actually happen.
It happens if, one, there is no air resistance, or two, the air resistance is small enough that it doesn't cause that big of an acceleration that we notice a difference. Okay? This example would work fine if you were driving in the parking lot going like 5 miles per hour, right? You could hold your hand out the window and you could do this with the ball out the window even though the car was moving 5 miles per hour, right? Yes, no?
Yeah, so if it's actually moving at 100 kilometers per hour,
Yes.
would it end up behind you?
No, not in this case. Why?
Because
What else is moving 100 kilometers per hour? The bus, and what else? You, the pencil, the bus, and what else? The air inside the bus is also moving 100 kilometers per hour. Does that make sense?
okay, last question.
Go
So
ahead.
if you stuck your hand out the window of
Yeah.
this bus, it wouldn't work.
That wouldn't work.
Okay.
Because now the air outside the bus isn't moving the same speed as you, so then it would experience air resistance, right? It doesn't happen in the bus because the air in the bus is moving the same with you, right? But the air outside the bus, if you stuck your hand out the window, right, then it wouldn't work. Technically it wouldn't work anyway, but if your bus was only going like 5 miles per hour, right, you might not notice it because the air resistance isn't that big. But if the bus is going 100 kilometers per hour, right, then you would notice a difference. Where would it land? Behind you, because the air resistance is pushing it this way, right? Does that make sense? All right, good there? All right. Let's skip then to Concept Development Practice Page 5-2. Concept Development Practice Page 5-2, dealing with Skelly the Skater. All right. At the top of Concept Development Practice Page 5-2, there are two data tables. And it says, Skelly the Skater, total mass of 25 kilograms, propelled by rocket power, as you can see here from this picture. It says complete Table 1 and complete Table 2. Table 1 has no air resistance. Table 2 has a constant 50 Newton resistance. So let's take a couple minutes and figure out, if it gives you a force, what would the acceleration be? If it gives you an acceleration, figure out what the force would be. All right? Let's take a couple minutes, fill in this chart, and we'll discuss. Go. All right. Up on the board are the answers for question number 1, part A and B for Skelly the Skater. Now we are getting into using Newton's second law, right? And we use two equations, really the same equation, just rearranged, to summarize Newton's second law, right? F net is equal to m times A, or A is equal to F net over m. Okay? Are we good with the answers on the board? If one or more than one of them don't make sense, raise your hand and let's talk about it. You're going to need to do this. Are we good with the second part where you have to subtract the 50 resistance? Okay. All right. Let's move on then, and let's move to the bottom of 5-2, and let's talk about this pulley system. So it says, block A on a horizontal friction-free table is accelerated by a force from a string attached to block B. Block B falls vertically and drags A horizontally. Both blocks have the same mass, M. Okay. All right, good there? Okay. So let's talk about this section. So it tells you in the problem, right, that block A experiences a force from the string attached to it that's also attached to block B. It also tells you what about the table? Frictionless. So are there any other forces acting on block A, at least in the horizontal direction? No. So what's block A going to start doing? If there's one force acting on it, Nick, before we talked about that in order to get net force 0, how many forces do you have to have? At least 2, right? But how many forces are acting on block A here? So could it be an equilibrium? Meaning that it has to be doing what? Accelerating. Very well said. Okay. Instead of just moving, right? There's a difference between moving and accelerating, right? This one has to be accelerating, right? All right. Ultimately, where is this force coming from? The force acting on block A, where is it coming from? Eris? Gravity acting on what? Acting on block B, right? So, we have another force in this picture that's gravity acting on block B. A lot of times, we will label gravity with a capital F and a lowercase g to represent that is the force caused by gravity. Okay? The force caused by gravity is calculated with a pretty simple formula. And that formula to calculate the force caused by gravity is m times g. What's m going to stand for? Mass. What does g stand for? What about gravity? Gravity's acceleration, right? Eris, if we multiply a mass times an acceleration, what should we get? Yes, but if we go back to the formula from yesterday, right? M times A equals what? Force, right? Or net force, right? So in this case here, if we take a mass and multiply it by an acceleration, we get a force, specifically the force caused by gravity, right? Eris, here on Earth, what does that G value stand for?
9.81.
Somewhere close to 10, right? So if we take the mass of whatever object it is and multiply it by the acceleration of gravity at that location, we will calculate how much force is actually acting on that object. Okay? Good there. Is gravity acting on block A? Yes. Okay? But, Suzanne, which way does gravity act? Up or down? Down, right? So if we go here, that's the other force that's acting on block A. But that's a different dimension than the red arrow, right? Red's horizontal, green's vertical. Is green the only vertical force that is acting on block A? If it was, what would it do? Not stop. If green was the only vertical force acting on A, what would it do? Which way, Nick? Down. Is block A accelerating downward? No. If it's not accelerating downward, what else does there have to be, Nick? How big is that force pushing it up, Nick? Equal to the gravity force, right? So here's what I'm going to do. I'm going to clone this bad boy right here, okay? And then I'm going to flip it up and down, right? And then I'm going to change its color just so it's not the same thing, right? Call it blue, okay? So really, how many forces does block A have acting on it? It really has 3 forces. But what are 2 of those forces doing to each other? They cancel each other out. So is block A accelerating? Yes. Okay? All right. Good with that. Okay. Because green and blue cancel each other out, let's just get rid of them. Okay? Now, gravity pulls on B. It makes it go down. But because of that, B drags A along with it. Okay? Good. How many blocks are moving in this problem? 2 blocks, right? So, what is the mass of this system have to be? 2m. There's 2 blocks moving. Each of them have the same mass m, so the mass here is 2m. Okay? Good there. But the force is only coming from gravity that acts on what? On B. The force that accelerates A plus B is the weight of B. Weight is a fancy word that we use to represent the force of gravity. Okay? So weight and the force of gravity are the same thing. That then allows you to answer question or letter C. What will the weight of B turn out to be? The weight of B is just m times g. It's the mass of that block times the acceleration of gravity. Good there? Okay. Here's where we start getting into some Newton's second law stuff. Right? Eris, if I let this ball go, what's it going to do?
Accelerate.
How fast?
It's 9 meters per second.
I was going to give it to you. I was going to give you 9.81 meters.
9.81. It's 9.81.
So, gravity acting on this ball causes it to accelerate at 9.81 meters per second squared, or close to 10 meters per second squared. But gravity on this ball is only making what move? On this example, the gravity acting on this ball only has to move what? Only has to move the ball. But in this example, the gravity acting on B has to move what? B and A. So Connor, what are we doing to the mass of this object? Increasing it over just letting B fall by itself, right? If we increase the mass, what else has to happen? Inertia increases. What kind of relationship does mass have with acceleration? Inverse relationship, right? So if mass goes up, acceleration goes down. So the acceleration here is going to be what? Less than g. Good there. All right. We good with that? Okay. Here's what I want you to do. The back of this sheet, 5-2, has 2 examples that are very similar to this one, except instead of having a block that is A and B that are the same, it has a block and a feather. All right? Assuming that the block is much, much heavier than a feather, right? For homework tonight, I want you to answer the questions 3 and 4 on the back page regarding the acceleration that that object feels because of the force of gravity acting on the hanging object. Good there? Okay. So for homework tonight, 3 and 4 on the back of that page. We'll talk about them in class tomorrow. Okay? Questions? All right. Beginning class tomorrow, open note quiz over forces, Newton's first law, Newton's second law.